Hi, everybody. How are things going right now? You guys had some homeworks over the weekend. Been working on these limit and limit-related ideas for a little bit now. I have one more section before I would say we've done enough for a test. So that's coming up here soon.
Are we gonna like a review?
We'll talk about like what the test format's going to look like and the types of questions, and I'll have some like AP practice stuff for you guys to work through. But I don't have like specific like here's a review. Mostly because I want you to review more than maybe what I would give you. Again, this is a class where we're aiming for a cumulative, like standardized test at the end. So I want you to kind of maybe do more than you need to on these early sections. So you over prepare now and it pays real benefits later on in second semester. I know that's kind of a crummy answer, and it's okay to be like, ugh, really? Hi, sorry. That's okay. But like, that's kind of the truth. I don't want to like sugarcoat it for you. Birthday. It's all the last one. But like, we'll, when it's time to describe what it is that I'm going to give you and ask for you to be able to do, I'll be reasonably specific on stuff. We haven't done that much in this first grouping of stuff to where it's just like, basically what am I going to be able to ask you to do? I'm going to ask you to do limits, continuity, like intermediate value theorem, squeeze theorem, and then what we do today, that's like kind of it in terms of things that we can ask about. There's not that much stuff, but like definitely enough stuff, right? Like there's enough variety of those things that it's like, that doesn't sound like a big list, but when I actually sit down and start preparing for this, it's like, oh yeah, there's like a lot of little tricks and details and stuff that kind of pop up to where it sounds like more than it is on a list. But so that's a coming. Do you guys have questions on stuff you want to ask about before we get rocking and rolling on this last one, David? 69 from 2.5. Sure. Here's my mouse. Just pull this guy in. Okay. Yeah. Now. So it says a Tibetan monk leaves the monastery at 7 a.m. and takes his usual path to the top of the mountain, arriving at 7 p.m. It's a long walk. Holy smokes. The following morning, he starts at 7 a.m. at the top and takes the same path back, arriving at the monastery at 7 p.m.
use the intermediate value theorem to show there is a point on the path that the monk will cross at exactly the same time of day. Okay. So I'm going to start by like defining two functions. I'll pick like it's going to be my path up, position on path up the mountain at time t. And we'll say PD of t is going to be our position on the path down the mountain at time t. Everybody's okay there. So PU of like 7 a.m., we're going to call that position 0. Everybody's okay with that? It's like the monastery. Maybe we can say equals, yeah, and path up at 7 p.m. I'm just going to call 1 for like it's completed. Everybody's okay? And my path down at 7 a.m. Well, there we're at the very top, and at 7 p.m. then we're at the bottom, right? Does everybody feel okay so far? So I'm going to take like P up minus P down. So at and this is going to be like my f of x. So at P up at 7 a.m., that's going to be 0 minus 1. And if I do the same thing at 7 p.m., I get -1 and +1, right? Is everybody okay so far? So if PU of t equals PD of t, i.e. the positions are the same at the same time, that's what it's asking about, right? That would imply that PU of t minus PD of t would equal 0. So if you look, we have a y value that's less than 0 and a y value that's greater than 0. So we're almost ready to just state the intermediate value theorem and be done. There's one other thing I would need, though, before I get going on that. I need to say that this function is continuous.
So I'm just going to say PU of t and PV of t are continuous because they represent a monk walking up and down a mountain. And unless this monk has like some superpowers where it can fold space or something, like we have continuity, right? Like that should be a common sense statement, but we need to make sure we say why it's continuous, and it's because of the nature of this physical problem. Now, if the monk can fold space or something, or teleport, or that's a different story. But I'm assuming this is a non-supernaturally powered monk. Fair assumption. Okay. So I can say, since f of 7 a.m. equal to negative 1 is less than 0, which is less than f of 7 p.m., which is equal to positive 1. There exists a C on the interval from 7 a.m. to 7 p.m. such that f of C is equal to 0. I should say by intermediate value theorem. And that's what we needed, right? So it's just like the hard part was getting to the setup of like, oh, what do I do with this? Well, let's start by defining some functions and like, what does it mean at the start and end? And like, you can use an arbitrary number to represent the start and end, or you could do like whatever, but like 1 and 0 just make it pretty easy to see what's going on. And then the trickiest thing was like, what am I trying to intermediate value theorem to? Well, if the positions are the same at the same time, if you can subtract one of them from each side, and it just needs the difference of them equal to 0. And once you make that leap, everything kind of falls pretty nicely out of that. Would I ask you to do something like this on an exam? No way, right? Perfectly reasonable homework problem, kind of makes you think about what do I need to do to this story problem to like squeeze out an intermediate value theorem situation, which I think is effective to, and valuable to think about. But in a timed test setting, I think that might be a bit much to ask. We have bigger fish to fry, and as valuable as this is, it's a sit and think about it, makes it valuable, not a hurry up and do it inside of this time, limited time window valuable, right? The scariest exams you'll get are the ones it's like 2 questions, you have 80 minutes. Or even worse, it's like, here's 2 questions, it's take home, you can use whatever you want. Those are the scariest ones because it's like, oh boy, there's no hope on anything helping me. It's like, I gotta do this all on my own, my big boy pants. Anyway, I don't want to scare you guys. I won't ask you to do that. I saw some other hands though when I asked for questions. Lucas, did you have 1, 2? Okay. 49? Sure. Is that felt okay though with what we did? And again, like once I started the setup, you probably were like, I see how this is going to end.
but like a lot of story problems, it's the setup that's the tricky part. We'll do a couple here and then we'll get to this last section, but we've done most of the hard parts for this, so it's going to be just a little bit of like vocab and rehashing skills that we've already developed. Okay. It says if f of x is equal to yada, 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 show that there is a number c such that f of c is equal to 1,000. So when I hear the phrase show that blah, blah, blah exists, this is going to be a theorem problem, right? Lucas, you good with that? So this is our two theorems we have to choose from: our squeeze theorem, intermediate value theorem. There's not much of a choice there. Squeeze theorem is not going to be real helpful to us here. This sounds exactly like an intermediate value theorem, like show that a function takes this value. So what my job is going to be is I want to hunt out two values of x when I plug them in, that one is less than 1,000 and one is greater than 1,000. Everybody's okay with that plan? All right. So I guess before I do that, though, let's just show that f of x is continuous. Why would I say f of x is continuous? It's the sum of two continuous functions, right? And I guess I'll say everywhere continuous functions. That is a polynomial and a sine. Right? Sine functions domain is all real numbers. The 10 out front doesn't change that. X squared is a polynomial. Polynomials domain is all real numbers. They're all both continuous across their domains. The sum of two continuous things is continuous. The domains are the same, so like you have continuity everywhere here. Is everybody okay with my explanation? And again, it doesn't have to be like you're not doing much here. You just have to say it, right? Just have to make sure you say it. This thing is continuous because, and like give a decent reason there, and I'm going to be good. The AP would be good, okay? But you do need to say it. All right. So if I think about sine or 10 sine x, I know that the biggest value 10 sine x can take on is 10, and the smallest value it can take on is negative 10, right? Everybody agree? So, well, f of 0 then I know is going to be less than 1,000, right? Because it could be 0 minus 10. Well, I know that sine of 0 is 0. So there's that. Everybody's good? Now I need an x value where I plug it in. I get something bigger than 1,000. So what would I pick there for, maybe 100? 100 squared is going to be 10,000. And then the worst that could be is minus 10. Everybody's okay? Now, if you have a calculator access, you could type in sine of 100 and like just press enter and get the number. But I know that this is greater than or equal to then 10,000 minus 10. Everybody okay with my reasoning there. I don't know what that number is if I don't have a calculator, but it doesn't matter. It's still like, it's at least that much, right? Okay. So I can say since f of 0 is less than 1,000, which is less than f of 100, the intermediate value theorem states there exists a C on the interval between 0 and 100 such that f of C is equal to 1,000. Adrian?
Did that really be if you could do the same thing, right? If you want
Yeah.
50.
Yeah. All you need is that you found two numbers between one below 1,000 and one above 1,000. So the 0 and 100 made no difference there. There are lots of choices you could have made. This is not a particularly tight bound if you were then to want to go search for that value of C. It doesn't really help you a whole lot. And in fact, my suspicion is since it's some kind of oscillatory behavior here, it may have more than one possible C. But yeah, I mean, certainly like 1 in 99 should have worked. There are lots and lots and lots of choices there. You probably could have done with like pies somehow and been able to like wriggle out of, like doing a computation in your head and getting a specific value. Right? If I did 100 pi, instead of 100, well, 100 pi is like 10,000 pi, which is way bigger than 1,000. And sine of 100 pi is going to be 0. And there you go. Now you have something you'd compute specifically, but like there's lots of choices. But yeah, there's nothing magical about the numbers I chose here. I just picked something that I could, came to mind. It was easy enough. I didn't have to monkey around with like mental math. Too bad. Aside from like squaring 100 and then making the argument that like, hey, that's at least that much. There wasn't a lot of mental math there. But again, if you had a graphing, like access to a calculator, like almost any number, you're just punching numbers in until you find one above and below and you're done, basically. That feel okay, guys?
Yeah.
We feeling okay on the IVT stuff? Did the Delta Math practice help on that a little bit in terms of like the language and what you need to do and how you say it? I hope it did. I thought when I saw that, I was like, oh, that is just perfect. Exactly what we need right now. All right. So I'm going to start in here on 2.6. And again, this won't be most of 2.6 we've done, like in one way or another already. One, because maybe I have a tendency to get ahead of myself and get excited. And two, this is just like kind of wrapping up the last bits of limit stuff. Miscellaneous limit stuff we can talk about before moving on. And start using the limit for what we introduced it for. It's intended use, maybe, in terms of calculus. So we'll start with a definition. It's a definition for a horizontal asymptote. So it says that let f be a function defined. It's not. It's for a limit to infinity. So it just says we can take a limit to infinity if that's equal to a constant. That means that the value is getting the function is getting arbitrarily close to that constant without ever actually crossing or reaching that constant. I shouldn't say cross, but ever reaching that constant. So examples of what this could look like graphically. You have like your classic asymptotic behavior. Notice it's not from our strict definition where it never crosses. Here we have crossing, but like the end behavior is horizontally asymptotic. Here you have your classic exponential horizontal asymptote. And here you have like a dampened harmonic function. So it's like a sine wave, but you notice after each wave, the height is getting lower and lower and lower. So you are getting an asymptotic behavior from both directions, above and below, but that one does give you the, what you're seeing there. If you think about like, if you drop a ball, every bounce it gets smaller and smaller and smaller and smaller until it's like basically resting on the ground. That's the kind of the same thing. If you modeled that behavior, you get like that dampened harmonic motion where it's just getting the wave shrinking down each period. And we can say the same thing if you're going to negative infinity, right? That if I take a limit to negative infinity, and that's the function's getting arbitrary close to some specific finite value, then we say the limit exists and it's equal to that finite value, right? We've done this already, right? We looked at limits to infinity way back in 2-3 when I kind of might have gotten ahead of myself and gave you all those infinite limit problems on there, right? So we've already kind of done this. And we're going to then take that previous two definitions and use them to define what we mean by a horizontal limit or a horizontal asymptote in our calculus class. So if the limit as x goes to infinity is a finite value, that y equals L is a horizontal asymptote. Or if the limit to negative infinity is equal to a finite value, then that y equals L is also a horizontal asymptote. At most, you can have two horizontal asymptotes. They can be different. They can be the same, or you can have none, where like the function just blasts off to positive or negative infinity, or like oscillates without ever dampening down to a single value like regular sine. Like that has no limit as x goes to infinity because it just doesn't settle down to anything. It just keeps bouncing back and forth between -1 and +1. As opposed to if you had like 1 over x times sine x, where that's going to now dampen down to 0. Is that okay? So let's take a look at this graph. And we're asked to find the infinite limits, the limits at infinity, and the asymptotes for the function f. So when we say infinite limits, we mean like the limit as x goes to a of f of x equals plus or minus infinity. Limits at infinity is the limit as x approaches plus or minus infinity of f of x. An asymptote is going to be the limit as x approaches plus or minus infinity of f of x equal to some specific finite value. So this is just a vertical asymptote, right? So if I look at my graph, do you see any vertical asymptotes there? How many? 2. It appears one of them is here, and the other one is here. Everybody agree with that? So for
this one, it looks like this is the origin right here. So we can say the limit as x approaches -1 of f of x is equal to if I look at this, both the left-hand and right-hand limits are going to positive infinity, so we'll just say that this is equal to positive infinity. Pretty good. Now you could write, the left-hand limit is equal to positive infinity and the right-hand limit is equal to positive infinity. That's not wrong. You could write that way as well. Let's look at this other one here. So the limit as x approaches. Now notice here at 2, one end of my graph is going to negative infinity and one end is going to positive infinity. So, yes, of course. So here I am going to write this as a left-hand and right-hand limit because the limit as x goes to 2, I would write, does not exist because the left-hand limit and right-hand limit are different. But if it wants me to list the limits at infinity, I want to list those limits that give me an infinite limit. I want to list all the limits that give me infinity or negative infinity. So the left-hand limit is the down, the right-hand limit is the up. Everybody feel good there? Got that. The limits at infinity, there can only ever be 2 of them, right? I'm always going to check as x goes to negative infinity and as x goes to positive infinity. So if I look at negative infinity, looks like 2. And if I look at positive infinity, looks like 4. So what does this tell me? That y equals 2 is a horizontal asymptote, and y equals 4 is a horizontal asymptote. Just like this would tell me that x equals -1 is a vertical asymptote, and x equals 2 is a vertical asymptote. Is everybody cool as to how we can look at a graph or the limits of a graph and identify whether it's like a horizontal or vertical asymptote? Okay. And the difference between infinite limit and limit at infinity, infinite limit is the limit equals positive or negative infinity. Limit at infinity is x is approaching positive or negative infinity. Okay. What's the limit as x goes to infinity of 1 over x going to be? 0. And what about negative infinity? Still 0, right? Again, probably the easiest way to think about it would have been like knowing what the graph looks like. Right? That's the graph of 1 over x. Clearly going to 0 at both ends. Everybody's good? For a rational function, how many horizontal asymptotes can it have? At most 1, right? For a rational function, like 1 over x, or x over x plus 5, or x squared plus 2x plus 7 over x plus 8, at most you can have 1 horizontal asymptote. It's either 1 or 0. Can't have more than 1 horizontal asymptote if you're a rational function. Everybody's okay with that?
So we saw that works for 1 over x. It works for 1 over x to any positive power, whether it's whole numbered or not. Now, the place where you have to be a little bit careful is if I have 1 over x to the r and I'm going to negative infinity. What do I have to be careful about there? Right, we have this extra stuff. If x is going to a negative value, what kind of exponent do I have to worry about on that x? I'd have to be careful if that exponent was a fraction with an evened number denominator. Why? Because it makes it an even radical. And can you take the square root of negative numbers or the even root of a negative value of x? No, right? So like if I do the limit as x goes to negative infinity of like this, it's, what is that? I don't know. Feels like you have a whole lot of discontinuity going on. That's real bad. Everybody's okay? Now, would I expect you to run into that? No, but that's why there's like this extra piece for negative infinity. Why is that stuff there? It's there to cover, something where you would have like infinitely many discontinuities, which we are not equipped to deal with in a class like this. That's like a real analysis type problem. That's like your capstone calculus class as an undergraduate. And you do a harder version as a graduate student, regardless of what kind of math major you're doing. Everybody gets to do it. All right, anyway. We're not doing this crap, right? We don't care. If you look at that, what's the limit? Excellent. 3 over 5. How'd you do that, David? Yep. You take the fastest growing thing from the numerator over the fastest growing thing from the denominator. If they're the same growth rate, then it's just leading coefficient over leading coefficient. Done. Right? You're boo-boo-ba-ba-ba-boo-boo. If I look at this guy, that is x squared on the inside. Yeah, root 2 over 3. Again, if you look at the numerator, the fastest growing part of that is the root of 2x squared. The denominator 3x. Root of x squared is just x, so you have root 2 over 3. And you're good. Questions on? We've just bulldozing through these, but we kind of already did this earlier. So if you're shaky or you're not sure, like, hey, I have a question, like, speak up, raise me a hand. Just be like, yo, I what? Something, stop me, and we can do more detail. How about something like this? It's not going to be 1. All right, so
This is hard because it's not a fraction, right? Everybody agree? If this is a fraction, we know exactly what to do. So here's the way I'm gonna do this. Is this plus 1 changing the limit at all if I'm going to infinity? So this should be the same as if I did that, right? Should get the same limit either way. And what's the square root of x squared? What's x minus x? 0. So it looks like it should be 0, right? Let's confirm that by looking at the picture. Forgot to do that. Okay, where's my thingy-majigger? You're all in my way. Go away thing. Do. Yep. It's gonna really put me through the whole thing here, huh? All right. And we need to do square root x squared plus 1 minus x. And then we're going to graph that out to like, should be plenty to kind of see what's going on. Sure as heck looks like it's going to 0, doesn't it? Everybody happy? So again, like you can do funny stuff with an infinite limit that you can't do with a finite limit, like where we can just like, does the plus 1 really matter? No. All right. And then do some simplifying from there, which is basically the same thing we did up here, right? We just ignored the plus 1 and took the square root of the top. And we ignored the minus 5 and then reduced and boop. Just we could do that one in our head. This one would have been a little bit less prepared to do in our head. But after seeing it now, it's like, okay, well, I can do that. I can do that. You just ignore numbers. Are you telling me that's okay to do? I love that. Yes. Thank you. All right. So here it says, evaluate the limit as x goes to 2 from the right of arctan 1 over x minus 2. So what I'm going to do is I'm going to do like a change of variable. So what is this piece? What's happening when we take the limit as x goes to 2 of 1 over x minus 2? What is that going to? Well, it's undefined, so it's either going to positive or negative infinity, right? Which one? If I take a number bigger than 2 and subtract 2 from it, is that going to be positive or negative? Positive. The number on top is positive. Positive over positive means I'm going to get a positive. So which infinity is it going to? Positive. Everybody's okay? So what I'm going to do then for this is I'm going to say, well, this is the same thing as just the limit as x goes to infinity of arctan x right? If this stuff is going to infinity, let me we'll not use that. Use a different letter. I can make a substitution and just say, okay, well, that's the same thing as like the inside going to y, or going to infinity, right? Which is what I've written. Everybody okay? Now this we can do. You remember what the graph of arctan looks like? Does anybody? Come on. So it looks like this. Do you remember or no? Okay. So the way, let's start with then tangent. So if I graph like the fundamental period of tangent, that looks like this, right? Where I have the vertical asymptotes, and then like, kind of looks like an x cubed stuck in there, right? And these were at negative pi over 2 and positive pi over 2. Yay or nay? Okay. So if I like draw in my line, like 1 over x, or sorry, y equals x, and I reflect that across, what am I going to be getting? Well, those vertical asymptotes become horizontal. We have like that. Anthony? Yeah, this is the same thing. We're saying that these two limits are equal. Because I just drew arctangent, not arctangent of 1 over x minus 2. I just drew arctangent. I don't know what the graph of this bloody thing is going to look like. It's going to be awful. I don't know. I don't care. I rewrote that this limit is the same as this. This I can handle because I know what the graph of arctan looks like. So I can just look at that infinite limit. Does that make sense? So what I did here was I translated this, like this limit that was a finite value into an infinite limit by doing a substitution. Does that, you see the distinction there? So I didn't plug 2 in anywhere. I just kind of like, oh, if I take the inside part, that's the part that's giving me problems. When 2 goes to, when x goes to 2 for this, I get positive infinity. So it's really just like, as the outer part goes to positive infinity, and that's what I evaluated. And again, I used a graph to kind of reason that out. Or you could do a table, like whatever. This is rough though, like really forced you to try to remember your trig and what these things look like. Unless you have a calculator access, in which case much easier to just like plot. I mean, you probably could have just plotted this thing if they're going to look at it and probably been okay. That was okay though, what we did? I know that was a lot of trig. And that's probably not all at the freshest part of our mind. I'm going to do like one of those because we're going to do this here. So here I have like the same issue, right? If I try to do like a direct substitution, I'm going to have like e to the something, like an undefined. Everybody's okay with that? So I'm going to take the same piece. I'm going to look at the inside chunk. So what is
the limit as x goes to 0 from the left of 1 over x going to be? Right, so obviously it's going to be an infinity because 1 over 0 is undefined. If I'm taking 0 from the left, all those values I'm plugging in are going to be negative over a positive. So that should be negative infinity. So this then just becomes the limit as x approaches, well, use y approaches negative infinity of e to the y. And that's a little hard because then now I'm having a negative in the exponent, right? So maybe I do one more, and I'll say the limit as z approaches positive infinity of 1 over e to the z. And now it should be pretty easy to see that that's just going to be 0, right? I see a lot of really unconvinced stares happening right now. Is this okay or no? Like, say something and we can explain some more. I can backtrack. I can talk more about what I did or how I knew what to do or what it is that I'm doing. But like, I don't know what's happening in your head, and the faces you're making are not faces that look very positive to me. So I want to stop here and just like, please give me some feedback one way or the other about how things are going. We just did something, and particularly like this part of the room looks really upset at me right now, and I don't know why. And maybe it's like, no, everything is fine, Mr. Kulik. That's just my face. I look upset when I'm thinking hard. That's okay. Like, at least just everything is okay or not okay. Just tell me, give me something, guys. Is this? Yeah, no? Yes. I'm happy to do that. So I look at this and I initially, like, that's a finite value, so I try like a direct substitution, right? Everybody's okay? The direct substitution in there, though, it gives me like an undefined when I do that. Everybody agree? When I plug 0 in for... So I say, okay, well, what if I just look at what's happening there when I, like if I push the limit inside and just look at the limit of the inner part, right? If I just look at the limit of that. Well, I get negative infinity there. So I say, okay, well, I can like rewrite this then. You know, by taking, you know, the limit and changing that to a negative infinity and getting rid of that and just calling it a variable, a new variable name like y. Now again, if I go and do this, I'm like, that's an infinite limit, but that thing's not a fraction, right? We feel much more comfortable if I'm doing a limit to infinity with a fraction. You guys agree? So when I'm plugging this in, these values for y are all negative values. When I have a negative in my exponent, what does that mean? It means a reciprocal, right? So I said, okay, what if then the infinity just goes to positive and I make the reciprocal? Now I have that fraction. I have a limit at infinity of a fraction. That's my best friend because I boo-boo-bob-up that and I know I can get an answer out of it. Does that feel better now as to like what and maybe I just didn't say it well enough here when I got excited and like, yes, Peyton.
No matter if it's like a fraction or not, isn't it always going to go to 0? Or like negative?
1 over e to the infinity. If I'm taking the limit as x goes to infinity of 1 over e to the x, that's going to go to 0. If I'm taking the limit as x goes to negative infinity of 1 over e to the x, that goes to infinity. So the sign on the infinity really matters for exponentials.
Okay.
And I think that's going to be a theorem here in a second. Sammy.
How does finding the limit to infinity solve the question of finding the limit to zero for both?
So this limit is equal to this one, which is equal to this one, which is 0. That's okay? I don't know if that was a very good answer, but that's what we did. Limit as x goes to infinity sine x. What's that got to be? What's the graph of sine x look like? What's the limit as that goes to infinity going to be? Does it settle down to a specific value? No. Does it just keep bouncing back and forth between -1 and +1? So the limit you'd say is, can you find a value? No, right? Is it infinite? No, it's stuck between -1 and +1. Right? Those are the y values. What happened to my graph? Just doesn't exist. Right? It's not settling down to a specific finite value, but it's not blasting off to positive or negative infinity either. It just stuck. Up and down, up and down, up and down, never settling down on anything, and never blasting away to positive or negative infinity either.
So there's no asymptotes on it?
There's no asymptotes either, yeah. So what this is called, this is like, because it oscillates. So if it doesn't settle down or just go blasting off, if it's just like, I'm bouncing back and forth and back and forth and back and forth, it's the other way a limit does not exist, right? So you have left-hand limit doesn't equal right-hand limit. Limit doesn't exist. Or if it's an infinite limit, if it just keeps bouncing back and forth and back and forth and back and forth, limit doesn't exist there either. And that can happen in non-infinite situations also. It's harder to come up with a function that you can write, but usually it involves a sine or a cosine or something. The limit as x approaches infinity of x cubed. What's that going to be? Infinity. Yeah, if you think about the graph of x cubed, it looks like that, right? Looks good. How about as x goes to negative infinity? This is true for all odd polynomials, right? Not quite, Mr. Kulik. Why not? If you tack a negative sign to the front, what's going to happen? They'd switch, right? Negative infinity, positive infinity. If they're even polynomials, they're both going to go at either positive or negative infinity depending on the sign on the leading coefficient. Right? Okay. Yeah. The limit as x approaches infinity of x squared minus x. If I try to direct substitute that, what are we going to get? I have infinity minus infinity, right? That's one of my indeterminate forms. That doesn't tell me anything. Is there a way to make that into a fraction? Okay, well, what good is that going to do? You can factor, sure. David?
I wouldn't. This is the better route, doing this. What am I going to do with this, though? What? Well, here's the idea. Remember your properties of limits? We can do this. Is that okay? Why, what does that accomplish? Well, if I do a direct substitution now, what am I going to get? Infinity times infinity, right? That's not indeterminate, just infinity. Which should, ideally, like, if I think about what the graph of x squared minus x looks like, should be infinity, right? Like, that confirms what we did there. But if we're doing it algebraically, if you don't have access to a calculator and you're like, what's the graph of this thing look like? It's more complicated than that. Sometimes if you're able to factor it into products, the only product you have to worry about is 0 times infinity. That doesn't tell you anything. Peyton.
Are we gonna have no calculator section?
Yes. But if you think about it, most of what we're doing is like, didn't really need a calculator other than to like make myself feel better if I look at the graph and it's like, okay, I feel like I did that one right. And you have a calculator, non-calculator sections because it's important that you're able to do both. And like having that tool and knowing how to use it is absolutely something I want you to be able to do. But we also have to like build up some confidence that I can do stuff without it. All right. How about this one? What's this going to be? Infinity. Very good. Fastest growing thing on top is x squared. Fastest growing thing on bottom is x. Basically turns into just x. The limit as x goes to infinity of x. It would not. Oh, would it be? Yeah, I think so. Yeah. Why, Alice? Yeah, so this is essentially that, right? Yeah, I think you're right. Nice catch. You're welcome. Good job paying attention. Did everybody see what she's saying? Yuck, right? Oh, good. This is the last thing. That's fine. I don't mind doing this yucky thing. It's the last thing. All right. Who remembers their polynomial stuff from pre-calc? Who's the polynomial master from pre-calc here? So I'm going to have zeros at -1, +1, and +2. Everybody agree? Okay. How is the graph going to pass through my +2? It's going to be a bounce. Very good. So I know it's going to look like that somehow. We'll do our connecting in a minute. How's it going to pass through -3? It's going to be a bend, right? Or it's going to like change concavity there. Or I guess it could go this way. We're not sure yet. Since it's an odd degree on that 0 that's greater than 1, it's going to bend to it. Because it's even degree. Right? X equals 2 is a degree 4. All even degree multiplicities have bounces. Sammy?
How do you get negative 3?
I have -1, +1, and +2 are my zeros, right? And -1 is coming from there. But it's used as a multiplicity of 3, right? It's being used 3 times. And then for +1, that just should go like straight through, right? But I guess we don't know if it's going to be that way or that way yet. Everybody agree? Okay. What degree of polynomial do we have here for the whole thing? 8. And the leading coefficient is positive or negative? Positive, right? Because I have x to the 4th, x to the 3rd, x to the 1st. It's going to be x to the 8th.
Oh, it's 4.
So that should be doing that. And that should be doing that, right? Okay? So this piece then would have to connect here. And that would have to connect there. And there's a good enough sketch of our graph. Now I didn't use any limits. Other than like, I guess I use these, but only in so as much as like they're going to be the same as the end behavior for a polynomial of even degree with a leading coefficient that's positive, but like, whatever. So that's 2, 6. My plan for next class is I'm going to give you guys just some problems to practice on. We'll do them like in groups at the board or something where like you have to get up and write something down. I can give you some individual feedback or whatever. Everybody's okay with this? Wednesday we'll talk about the test and that stuff. And then Friday is my prospective test day. Does that feel reasonable, timeline-ish? It's not hammering you with like an AP bio test on the same day right yet, at least as far as you know. Okay. This is me trying to be concerned about like you guys. And I'm going to tell you something. Again, none of you guys know me very well. I don't care when stuff gets done. If the test day looks like a bad test day, just tell me. We'll teach something new on the test day. The test will stay as is, and just go to the next class period. I don't care. That's fine. It's not a big deal to me. I have no problem doing that stuff, but you got to let me know. Okay? If it looks really bad, and you're like, can we kick the can on this a day because I just found out that I have 8 other things that are due this day or whatever, and it's like, yeah, I can just start teaching the new stuff, and we'll do the test later. That's not a big deal to me. If it helps you guys out, I'm happy to do that. But you gotta let me know. I know none of you know me that well. The due dates, I do not care about this in general. Hence my homework policy. Hence what I'm telling you about the test. Like, it'll still be there 2 days from whenever we're planning on taking it. As long as we're not wasting class time, I'd rather put you in a position where you feel like you can do well than like shove it down your throat because for whatever reason I feel like the test needs to happen before we teach new things, which I don't feel that way at all. Is that okay with you guys? Feel good? Everything going okay today? Yeah? The last thing I want to say is that I have put in some sample multiple choice questions that I've taken from the AP website. So there's 30 or so of them. I also have the answers so you can kind of check yourself as you're going along. There will be multiple choice questions on your test that I will give you. They will be in the style of the AP questions here that I've listed. Okay? So as part of your review process, I would try to plow through and do these things. If you have questions on stuff, we can certainly come and
handle that in the future. You know, the next day or two in class. Happy to take questions from this stuff also. I want to point out that those are there. I have a test 1 written down. You should not look at this yet. I should probably delete this. The test one that I wrote last year is gone. Like all of my files from the past died at one point, and that was amongst the casualties. So this format that's described here is not necessarily the format that you're going to see on your test if you're looking ahead at what the test format's going to look like. I will update this. I will tell you once I've updated it, but don't look at this right now because I'm having to rewrite the test. And it might not look the same way as what this is describing, although I'm going to look at this when I go and write my test and try to make it somewhat similar. But every year we update things, you know. This will be a big update because I don't have the original that I worked from the first time. So, everybody's okay? The test will be in 2 parts. We'll have a no calculator part and a calculator part. So you'll turn in the one part and pick up the second part and then get your calculator. Usually we start with the no calculator part. Adrian?
So if you have a test Friday, are you gonna have like a 2.6?
Yeah, the 2.6 homework was there. It's not due until Sunday, right? It's part of Sunday's due date homework, along with that Delta map that we looked at last week, the IBT and the stuff on it. That'll be Sunday's problem set. There won't be anything else on to it because we'll cover more material just now and then. Obviously, should you do this before the test? Yes, but like, I don't need to see it until Sunday. Does that make sense? Yeah, Mia. Should we have a homework quiz next class? What do you guys want to do? What have we had? 3 already in this chapter? You tell me, you just saw what we did. No? Okay. I was going to say this looks like the stuff you already know how to do. Feels like it should be easy, but okay.
All like the last one, sure.
The last one? Yeah.
Oh, I think part of the last one.
Okay. So let's not then, eh? Seems like there's no consensus. To be quite honest with you, like between getting problems together for you guys to practice next time and trying to write the test for Friday and the grading and everything else that's going on, I'm kind of underwater enough to where like, yeah, it sounds good to me too. It helps me out. So let's go ahead and do that. I know.
Are they different for every class too?
I usually make 2 separate versions that are equivalent, and then we'll probably end up writing a 3rd for absent, for the people that elect to be like David. Oh, okay. I'm gonna stop my recording.